All right, let's go.
Number 7. The Methuselah Star, a star that was, according to the math, born before time began. In 190 light-years away in the constellation Libra sits a star called HG 140283. Astronomers gave it a nickname decades ago that tells you everything about the problem it caused: Methuselah, after the oldest man in the Bible. In 2013, using precise distance measurements from the Hubble Space Telescope, a team led by Howard Bond calculated the star's age with unprecedented accuracy, factoring in its brightness, its composition, and its internal structure. The number that came back was 14.5 billion years old, with an uncertainty of plus or minus 800 million years. The universe, according to the best cosmological measurements available, is 13.8 billion years old. A star, sitting close enough to see through a decent pair of binoculars, appeared to be born roughly 700 million years before the Big Bang that was supposed to have created it. Not a small fringe discrepancy, a single, ordinary, nearby star casually contradicting the origin of everything. The resolution came down to that uncertainty range. 14.5 billion years minus 800 million years lands at 13.7 billion years, safely younger than the universe itself, just barely. Refined measurements since have nudged the central estimate down further, and the current consensus is that HG 140283 formed within the first few 100 million years after the Big Bang, making it one of the oldest stars ever directly measured. Not an impossible one. But the story matters for a reason beyond the star itself. It is the clearest public demonstration that measuring the age of anything in deep space, even something sitting almost in our own cosmic backyard, comes with error bars wide enough to nearly break the entire timeline of the universe by accident.
Number 6. The ancient globular clusters. The original age crisis, decades before Methuselah. Long before HG 140283 made headlines, astronomers had already lived through this exact panic once. Globular clusters are dense spherical swarms of hundreds of thousands of stars, among the oldest structures in the Milky Way. Through the 1980s and into the 1990s, age estimates for clusters like M92 and others routinely came back between 16 and 20 billion years old using stellar evolution models available at the time. At that same period, measurements of the Hubble constant, the expansion rate of the universe, were producing age estimates for the universe itself closer to 10 to 13 billion years. Depending on which measurement you trusted, the oldest star clusters in our own galaxy are flatly older than the cosmos containing them. This became known, seriously, in academic papers as the age crisis of cosmology. It was not a fringe complaint. It sat at the center of mainstream astrophysics for years because it meant one of two foundational pillars of cosmology had to be wrong. Either stellar physics was miscalculating how fast stars burn through their fuel, or the expansion rate of the universe was being measured incorrectly. The resolution took most of a decade and required corrections on both sides. Improved distance measurements to globular clusters using better calibrated standard candles brought stellar age estimates down closer to 12 to 13 billion years. Simultaneously, refined measurements of the Hubble constant and later, precision data from the cosmic microwave background through missions like WMAP and Planck pushed the age of the universe itself up to the now standard 13.8 billion years. The crisis quietly resolved by 2003. But it set the template for every impossible object story that has happened since. Something looks older than the universe. The universe was probably measured wrong, or the object was. Sometimes both.
Number 5. The universe breakers. 6 galaxies that should not have had time to exist. In February 2023, a team led by astronomer Ivo Labe published a discovery using the earliest data returned by the James Webb Telescope that astronomers themselves nicknamed the universe breakers. 6 candidate galaxies observed at a point when the universe was only 500 to 700 million years old, roughly 3 to 5% of its current age.
Under standard models of galaxy formation, structures this young should be small, chaotic, and just beginning to form their first generations of stars. Instead, these 6 objects appeared to contain stellar masses comparable to, and in one case, potentially exceeding, the mass of the entire Milky Way today, a galaxy that has had the full 13.8 billion years to build itself. One candidate appeared to hold roughly 100 billion times the mass of the Sun in stars, packed into a galaxy roughly 30 times more compact than a modern galaxy of similar mass. Astrophysicist Joel Leha put it plainly at the time: these things are in conflict with 99% of models for cosmology. Astrophysicist Mike Boylan-Colchin calculated that producing this much stellar mass this early would require nearly every single atom of ordinary matter available in that region of space to have converted into stars, an efficiency that has essentially no precedent anywhere else in the observable universe. Follow-up observations since 2023 have complicated the picture rather than resolving it cleanly. Some of the most extreme candidates turned out to be closer and therefore less impossibly early than first measured, often because the light from a feeding supermassive black hole at a galaxy center can masquerade as starlight in the initial data. But as of 2026, several of the original universe breakers have survived closer scrutiny, and continued JWST observations are still actively testing whether even one of them holds up completely, because researchers on the original team have said plainly that even a single confirmed survivor is a genuine problem for the standard model of cosmology. Number 4. The black holes that grew up too fast. A problem weighing over 1 billion suns. Supermassive black holes are supposed to take time. In standard models, they grow gradually, feeding on gas and merging with other black holes over billions of years, slowly climbing from stellar remnants to the monsters that anchor galaxies today. That timeline has a serious problem. Multiple quasars, the blazing accretion disks that form around actively feeding supermassive black holes, have been detected at redshifts corresponding to less than 1 billion years after the Big Bang, already carrying masses exceeding 1 billion times that of the Sun. The quasar SDSS 0313-1806, confirmed in 2021, sits at a point corresponding to roughly 670 million years after the Big Bang, and already carries a black hole with more than 1.6 billion solar masses. In 2023, a JWST observation identified a black hole candidate nicknamed UHZ1, dating to around 470 million years after the Big Bang, already comparable in mass to its entire galaxy, a ratio that should be physically impossible under standard growth models, where the galaxy is expected to vastly outweigh its central black hole at every stage. Growing a black hole from a stellar mass remnant to 1 billion solar masses in under 1 billion years requires sustained feeding rates pushed to or beyond the theoretical maximum, called the Eddington limit, for the entire duration. Doing it more than once in multiple independent objects found across different regions of the sky is not something the standard model of black hole growth was built to explain comfortably. Proposed fixes include the idea that some of these black holes may have been born unusually massive to begin with, collapsing directly from enormous primordial gas clouds rather than starting small, skipping several intermediate growth stages entirely. That remains an active, unresolved area of research as of 2026, not a settled answer. Number 3. The galaxies that already had a shape. Structures that were not supposed to survive their own youth. Standard models of galaxy formation predicted something specific about the early universe. Young galaxies should be chaotic, blobby, irregular, the kind of structure produced by frequent, violent collisions, because the early universe was a crowded, turbulent place where galaxies merged constantly, and delicate structures like spiral arms and flattened disks should get destroyed almost as quickly as they form. JWST imaging of the early universe found something different, a significant population of well-formed disk galaxies, complete with the kind of organized structure that should require a long, relatively undisturbed history to develop, showing up far earlier and far more frequently than predicted.
One analysis found disk galaxies appearing roughly 10 times more often in the early universe than standard models anticipated. This is a quieter problem than the mass crisis of the universe breakers, but a structural one that cuts just as deep. It is not simply asking how galaxies got so heavy so fast. It is asking how they got so organized so fast, in an era that was supposed to be defined by chaos. Researchers studying this, including work published through 2025, have proposed that early galactic disks may have been more resilient to collisions than previously modeled, or that the merger rate itself in the early universe has been overestimated. Neither explanation has become the accepted consensus. As of 2026, this remains one of the open threads researchers are actively trying to reconcile alongside the mass problem.
Number 2, the Hubble Tension, the crack underneath every age on this list. Every object on this list gets compared against one specific number, the age of the universe, 13.8 billion years. That number itself is not as settled as it sounds. There are two independent ways to measure how fast the universe is expanding, a value called the Hubble constant, which is directly used to calculate the universe's total age. Measure it using the cosmic microwave background, the afterglow of the Big Bang itself, and you get a value around 67.4 kilometers per second per megaparsec. Measure it using nearby exploding stars and pulsating variable stars, building what is called the cosmic distance ladder, and you consistently get a noticeably higher number, closer to 73. These two methods should agree. They do not. The gap between them, called the Hubble tension, has grown more statistically significant, not less, as measurement precision has improved over the past decade, now sitting at a confidence level physicists normally treat as a genuine discovery rather than a rounding error. This matters directly for every impossible early object on this list. If the true expansion rate of the universe is closer to the higher, locally measured value, the calculated age of the universe itself would need to shrink, not grow, which would make problems like the universe breaker galaxies and the earliest supermassive black holes even harder to explain, not easier. Every impossible early object gets measured against a ruler that physicists openly admit might currently be miscalibrated, and nobody yet agrees on which end of the ruler is wrong.
Number 1. What these objects are actually telling us. Not that the Big Bang is wrong, that something around the edges still is. Here is the honest position as of 2026. Not one of the objects on this list has been confirmed as genuinely, unambiguously older than the universe. The Methuselah Star's error bars allow it to fit. The ancient globular cluster crisis was resolved through better measurement on both sides. Several of the original universe breaker galaxies have already had their extreme ages revised downward under closer inspection. But the pattern across all of them is not nothing. Stars, galaxies, and black holes keep showing up right at the ragged edge of what the timeline allows, over and over, across completely independent lines of evidence, using completely different instruments, built by completely different research teams with no reason to coordinate a shared mistake. The Big Bang model itself, the idea that the universe began in an extremely hot, dense state roughly 13.8 billion years ago and has been expanding ever since, remains extraordinarily well supported by multiple independent lines of evidence that have nothing to do with any object on this list, including the cosmic microwave background and the observed abundance of light elements like hydrogen and helium. Nobody serious is proposing the Big Bang to not happen. What these repeated near misses are pointing at is something narrower and, in its own way, more interesting. Our models of exactly how fast stars form, how fast galaxies assemble structure, and how fast black holes can grow may all be tuned slightly wrong, consistently in the same direction, toward underestimating how quickly the early universe could build complicated things. Every object on this list is a small crack in the same wall. None of them have brought the wall down, but cracks that keep appearing in the same place across different instruments and different research groups over more than 30 decades are usually not measurement noise. They are usually where the wall is actually weakest. 7 objects that at some point appeared to break time itself. A nearby star whose age briefly outran the universe that made it. A generation of stellar clusters that forced astronomers to rebuild both stellar physics and cosmology at once. 6 galaxies too massive and too organized to have grown up that fast. Black holes that hit 1 billion solar masses before the universe had time to build them properly. Disk galaxies with structure they were not supposed to have earned yet, and underneath every single one of them, a ruler measuring the age of the universe that 2 independent methods still cannot agree on. None of it means the Big Bang is wrong. It means the story of exactly how fast the universe learned to build things is still being rewritten, one impossible object at a time. Subscribe to Cosmic Hives. See you in the next one.